Okay, welcome to the Permittivity of Free Space remake video. There was some, now I'm going to spell it wrong. Permittivity of Free Space. Ooh, like it sounds like really intimidating. But what does it actually mean? So we're going to start off with a little assumption. And the assumption is that you understand the fact that if I have two oppositely charged objects placed in space somewhere nearby each other, that you will get an attractive force acting between them. Okay? So let's put a positive sign on this one and a negative sign on that one. Okay? The tradition is that we draw what are called field lines based on what force a positive charge would experience if we place it inside the area where these things are present, right? So if I take this thing and I plop it right in between here, it's not too hard to see that you're going to get a field line that looks like this. Anywhere along this pathway, you're going to get a rightward force acting on that object. So the field line is just going to show you that. What force will a positive charge experience when it's placed somewhere between these objects? And if you think about it and work it out, you eventually will construct that the field's got to look like this. Okay? The strength of the field is stronger when we're closer to the objects. Remember the inverse square relationship as you move away or towards sources of fields. And therefore, you know, or the other way to think about it, I like to think about it like a wind. There's a wind blowing out of positive and blowing into negative, and that wind is stronger the closer you are to this object here. Okay? And then from this idea, from essentially people experimenting with this, charging up objects and seeing how they attract and repel from each other, not just people, a person in particular, you come to Coulomb's law. So I don't know if the law in whole was discovered by Coulomb, but he definitely worked towards figuring out the relationship between the amount of charge and how much attractive force you're going to find between two objects that are either oppositely charged or charged in the same manner. So if I have a plus, and let's say a plus, and we know the distance between them, which we'll call r, okay? Coulomb told us that the force, and we'll call it the electric force of, in this case, repulsion, is, first of all, it's proportional to the amount of charge stored on these things, on these objects. We'll assume they're insulators and they're charged up, like say they're balloons, for instance, balloons with equal charges. Well, they're going to repel each other, and Coulomb worked out the relationship between the fact that if I say double the charge on one of them and leave the other one the same, I'm going to get double the amount of repulsive force. Kind of makes sense. And he also figured out that you had an inverse relationship between the distance, and particularly the square of the distance, and the amount of force exhibited on these charges. I'm not sure if Coulomb himself worked this out, but the law associated with Coulomb, which we call Coulomb's law, is Fq, the amount of force, is equal to K QQ over R squared, where K is called Coulomb's constant, these Q's are charge measured in coulombs, and R is the distance between the objects measured in M. So if you don't know, what is a Coulomb? Well, a Coulomb is basically the amount of charge deposited, or transferred, I guess, by a 1 amp current in 1 second. I like to kind of think of it like a fire hose, sort of, okay? And it's just like, it's spewing out charges, like a spray. This isn't really how it works, but it's fun to think about it like this. Okay, and you get 1 Coulomb okay, in 1 second. All right? So then, I should be careful. Yeah, 1 Coulomb per second. So 1 amp equals 1 Coulomb per second. Or 1 amp you could think of as equal to 1 Coulomb per second. Or a better way to think about it, because the amp is the fundamental unit of charge, or of electricity, I guess, in SI, is that actually a Coulomb is 1 amp second. So 1 amp acting for 1 second. That's how much a Coulomb is. Okay? So when we look at charge, we always measure charge in terms of coulombs. It's an amount or a number of elementary charges collected in a certain spot. That's how we view charge. And the amount of charge in 1 Coulomb is a big amount. 1 Coulomb is equal to 6.2 times 10 to the 18 elementary charges. An elementary charge is the amount of charge on 1 electron or 1 proton. If it's positive charge, if it's a bunch of protons, then it's positive charge. If it's a bunch of electrons, then it's a negative charge. Okay, so here's the question. Looking back at this picture, right, and looking at this formula, we might say, okay, if we know the amount of charge here, I don't know, let's say this is like 1 microcoulomb, and this is like 1.5 microcoulombs, and this R value, or the distance between them here, is like 1 meter, okay? We could simply just take this formula, and we could just pop this in there, okay, and we could work out a value for the amount of force, and in this case, it's attractive force between the two objects, or in this case, here, the amount of repulsive force between the two objects, okay? This is true as long as you stay in a vacuum, okay? In a vacuum, this holds true, okay? But you got to modify it a little bit if we're not working within a vacuum. So let's say you take your two charges and you submerge them in, say, some sort of insulating oil, or even pure water with no ions dissolved in it, which is a good insulator. Do you still get the same exact amount of force when you submerge this in liquid, or like encase it in plastic, or put it inside wood, or whatever? Does that force work out to be identical to what would happen if you did it in pure empty space? And the answer is no. It will modify how much force you get. So the question is why? And the why is because if there's something in between these two charges that is not free space, that impacts the way that the field permeates through the area between the two things. It changes, if you want, the permittivity to the field. So we got to look at that. How does it change? All right, so I want to talk about this concept of permittivity here. And in order to do so, let's just keep our Coulomb's law handy so we can have a look at it. And the first thing that we want to talk about is the fact that this does not change if you're in some insulating material. That is still true, and this is still true, okay? These still hold, okay? But what changes has to do with this. So let's just get this slightly more, I guess, precise. So it's actually like 8.99. The key is, well, what units are we talking about here? So what we've traditionally written this down as is as newtons, right? Because you got to end up in terms of force. You got to cancel off 2 Coulomb charges, and you've got to divide away by 2, or a square of radii, I should say, okay? So that'll cancel out and we'll be left in terms of newtons. Can we actually get this into a more fundamental form if we wanted? Sure we could. Newtons is not fundamental, and we know that a newton is a kilogram meters per second squared, right? Multiplied by the -2 for coulombs, multiplied by meters squared. Can we collect up any more units? I don't think we can. Oh yeah, sorry, we can. You're right. So we could go meters cubed per second squared per coulomb. And also, coulombs are amp seconds, right? So, and they're both multiplied by, or raised to the power of -2. So now you've got this, which gets us to this. And actually, we're kind of getting farther away from what I actually want to deal with here. But this is sort of a fun thing to sometimes go ahead and do, just to see if we can. And that, I think, should be to the -4 when we're done, when we've collected them all up. I hope we're right. I feel like I need to double check this. Right. And of course, we got a little carried away there, or I did, not you. This is all times 10 to the 9. We can't forget that. All right. Perfect. Do not forget that it's 8.99 times 10 to the 9. It's not just 8.99, okay? It's a really big number. Remember, electric fields are like orders and orders of magnitude greater than gravitational fields. All right, I'm going to keep going here. Keep going with this. So it turns out, again, remember what we're after here is we're after looking at what is going to change if we move from empty space between our two charges, whatever they happen to be, and we say submerge them in water, or we put them in like, I don't know, like molten rubber, say, or something, or in water, right, in pure water. If we put them in there, what happens to the force between them? So the first thing is we need to rewrite K in a slightly different form. So it turns out that you can also write K as equal to, let's check my notes here so I do it correctly, 1 over 4 pi over E naught. Okay, where? This is called the permittivity of free space. Okay? E naught is the permittivity in a vacuum, hence the kind of free space thing. You might say, but why the 4 pi? What does that have to do with anything? Where else have you seen, what was that? 4 pi before? Someone said it?
Surface area.
Right. Right. If we have a sphere and we're dealing with fields, right, that emanate out in terms of like spherical shells, okay, and we have our fields passing through, I guess if you want, subsequently larger spheres of area, it kind of makes sense, and I can't tell you a ton more, but I know that the surface area of a sphere is 4 pi r squared. That is playing a role in here, and that has to do with K and the fact that K spreads out, or space spreads out, if you want, in ever-increasing spherical shells from the central point charge that we have here. So as we get farther out, the field decreases in terms of strength relative to r squared. The permittivity also relates to this ever-increasing spherical shell as you come out from there. I can't give you a lot more information than that, and I can't really derive anything else from that. But I know you can write K in terms of the area of a sphere and this idea of permittivity of free space. So what is the value of E naught then? Well, E naught turns out to be, first, is it going to be big or small? Permittivity of free space. Remembering what K is. Big or small? Super small, right? You got to divide into 1 like to the power now like 1 billion times, right? So it's going to be small. So we got 8.85 times 10 to the -12 per Newton per Coulomb squared to the power of meters to the -2. Now look at the units and compare the units to what you had here. Actually, what you had here. I don't know why I went to all this trouble, because all I really needed was this. Okay? K, and this of course is going to probably make sense to you as soon as you see how this is set up. Looks like that. And it's an inverted value of that, and it's modified by the 4 pi. So it's related to K as it stands, but it's modified to I guess, to allot for the fact that we've now got an inverse relationship to K itself. So you can always find the permittivity of free space if you know K, and you remember that it's related by 4 pi to the value K, which is Coulomb's constant. Okay, so this idea here, this little constant is the permittivity of free space. All substances that are not free space have their own permittivity constants. Okay, so for example, some rubber has an E value. So notice it's not E naught, it's the permittivity of this particular substance. Let's say it's equal to 5.83 times 10 to the negative 11, like that. Okay, so some rubber has that. So let's say what I've done here is I've taken, just to make it like slightly more realistic, say I've taken my 2 balls, and instead of putting 2 balls in water, just to make this a little more realistic, I've taken 2 parallel plates. Okay, so let's see here. All right, and these parallel plates are hooked up to some source, and one side is positive and one side is negative. They still have some charge associated with them, okay, and therefore they're going to attract to each other. So in free space, we could figure out, based on the distance between them and the amount of charge they have, the amount of attractive force between them. But now what we're going to do is we're going to take a block of some rubber and we're going to plop it between these two things so that the field has to permeate through the block, right? So there's going to be a different permittivity as the field permeates through the block of rubber than it would have had it been allowed to permeate through empty space, or even for that matter, air. So why should that change the value of force between these two things? What's going on inside the rubber itself that makes it have a different permittivity? What's the deal? Why does it interfere, if you want, with the permeation of that field? All right, so the first thing is, this is considered to be a dielectric. Rubber's a dielectric, which means it does not transfer, it does not freely transfer current through it. If you did have current available to be traveling through this, in other words, if I put like tin foil in here or some other metal, I would just instantly make my charges equal on one side and the other. The current would just flow to equalize charge and I'd have no field anymore at all. The field would break down to nothing. So this only works, it's only dielectrics that have permittivity values. And then what happens is, well, this rubber is made up of little atoms, and each atom has positive and negative charge associated with it, and it's locked up in the rubber polymers. The charges can't really flow anywhere, but they can kind of like reorient, right? So you might expect the electrons to spend a little more time towards this side than they do towards the other side, and that sets up tiny little bunches of mini fields all within this dielectric. The overall cascading effect of that is that the permittivity of the overall field through here is changed. It's modified by the fact that it has to pass through matter that is itself made up of tons of tiny little electric field generators, if you want, little atoms that contain their own electric fields that can be modified by the external force, or by the external field. Okay, so you'll notice that the permittivity of the rubber is quite a bit higher than the permittivity of free space, okay? Which maybe makes sense because you're going to end up finding the value of it on the bottom. So let's see about how we actually like use this value right here. So what's been come up with is this concept of relative permittivity, which is just this: the permittivity of the particular object, in this case the rubber, and its ratio with the permittivity of free space. So you get a relative permittivity of this particular rubber as the following. Okay. So a couple of things to notice. Relative permittivity is unitless. There'll be no units because all the units cancel off. And in this case, you get a value of about 6.6, I think. 6.6, if you do the math. So the relative permittivity of this rubber is 6.6. Its actual permittivity is here. And the permittivity of free space is here. So I guess a way to think about it would be that permittivity is 6.6 times that of free space. Okay? And you can see that something with the same permittivity as free space is going to have a value equal to 1. Okay? So free space has a relative permittivity of 1 because it's just itself divided by itself. Are you with me so far? So I have a little chart I could put in of some permittivities just, I guess, to, I don't know, help us understand a few. Have to think about what I'm doing here. Uh-oh, where did that go? Okay, so here's some permittivities. So first of all, our dielectrics will go in here. Whoops, come here. You move over here. Ah, sorry, having trouble. Always fun when I have trouble, isn't it? Okay, so this will be our insulators. Got to be insulators. And these will be our relative permittivities. Okay? So vacuum. Ooh, can't see that. That's 1. Air. Air is pretty close to vacuum. It's that. Okay? PET, which is a type of plastic, looking at about 4. Paper, about 4. What else do I have? Concrete, about 4. Rubber, about 6. And water is about 80. Why do you figure like water might be so large comparatively? What do we know about water? Polar. So its polarity has to do with the fact that we're dealing with water being able to flip-flop. If you put an electric field across water, its dipoles are going to line up. They are little fields themselves, and they're going to like mess around with how that big field permeates through the water. Let's see what we can do with this. So now what we can do, now what we have the power to do, is we can just reformulate Coulomb's law in terms of whatever medium we want to plop it into. Not just, say, air, which is relatively or pretty close to the same as vacuum, but inside any. Do it in water. We can actually get values that are real. So let's just see if we can figure this out. All right, so we've got FQ. That was K. QQ over R squared, but we also said that K could be formulated as 1 over 4 pi E naught. So where I see K, I can change it with 1 over 4 pi E naught, which is going to do this, right? So just for the people who struggle a little with algebra, we'll write it like this first. That's fair to do. So then we get this 1 over 4 pi E naught QQ over R squared, and we rewrite it like this: QQ over 4 pi E naught times R squared. Okay, so there's the reformulation of Coulomb's law. Now again, this is in terms of E naught, all right? Which doesn't really help us. This is going to give us the exact same answer that we got when we just put K in directly. But we want to know what we can do if we have a list of, say, like relative permittivities. Can we modify this formula to deal with that? And the answer is yes, of course we can. So how are we going to do it? Well, we know this is true, right? Those relative values were got by taking the permittivity of the substance and dividing it by E naught. So what we can do is we can do a slight little modification here. Okay, so if we're not in terms of E naught, right? If we want to talk about a particular substance, we need to use E. But if we don't have E, we can simply take the relative value and multiply it by E naught to get E. So E then is going to be found as, as, I keep saying E and I should be saying epsilon. It's not really an E. But E is going to be found as the relative value multiplied by the permittivity of free space. So, Coulomb's law, with a dielectric where you know the relative permittivity, you know the permittivity of free space that you'll be able to find or look up. Okay, and this is the permittivity proper of the substance. So the last thing we have to do is just write our final formula where instead of E naught, we have E, but it's based on relative permittivities, because you're going to get a list of relative permittivities rather than actual permittivities. It's just one of those things. It's just how it's done. So you get this. Q over 4 pi relative times free space over r squared. And this is the formulation of Coulomb's law for any dielectric if you know the relative permittivity of that dielectric. All right, let's try and use it and see what happens. So let's do this. Say we have 2 plates. Okay, 2 plates. Let's say they're 1 meter apart. Okay, and let's say that the charge on them is 1 microcoulomb and 1 microcoulomb. And let's find the force FQ in air. Actually, let's do vacuum. Although basically vacuum and air are so close to the same, it doesn't really matter. And let's do it in pure water. Okay. And you can actually use this formula in both situations, right? The ER of vacuum is just 1. So you put 1 in there and multiply by E naught. You should get the exact same thing you would get if you did FQ equals KQQ over R squared. You'll get this. You should get the same answer. And then remember, if you're doing water, you got to put 80 in here. So 80 goes here. So the force becomes weaker, obviously, between those two things at that point in time, because you get a larger number on the bottom. Make sense? So we'll just pause and we'll solve for values, and then we'll come back. Okay, so here's your final values. In vacuum, you've got 8.99 times 10 to the negative 3 newtons, and in water, 1.12 times 10 to the negative 4. So a significant drop in the amount of attractive force between those two plates.